So now we have this incoming phase. It's offset from the VCO frequency, and it has its own phase offset. And we want to convert this. Let's convert this into the S domain, because the video before the last one, that's what we had done, right? We had rewritten our whole system in the S domain. So let's figure out how this incoming phase could be rewritten in the S domain. So using this, and again, came from a table of Laplace transforms in the electric circuits text, right? We can quickly see that this T can be transformed into 1 over S squared, and then this is some constant, can be transformed into 1 over S when we go into the S domain. Okay, so now we have an expression for the input phase. Okay, so hopefully this is starting to make sense, because one of the places we left off at in this previous video, right, was here. We left off here, and we had not figured out what this would look like in the S domain. We were kind of left that hanging. Then we took a short break to look in the time domain to figure out what our input phase should be when it varies from the VCO. Now we've got this input, and we're turning it into the S domain. And we can see now that based on this S domain, we can rewrite the input in the S domain like this. Okay, great. So now let's consider the special case where the loop filter is just equal to 1. Okay, and that's going to simplify this a little bit further, because we just figured out what this is. And then if we simplify for a simple case, for simple analysis, we'll assume that this is equal to 1. So this filter function is just a passing filter, and then A and K remain those constants. So if the input in S domain, which we just found, is this, and if we substitute that in, right now we see that the S domain here goes here, and so we have two somewhat complex terms that are multiplying each other. So if the phase error when incoming mismatches the VCO, this is what the phase error is going to look like. So the mismatch comes from, we had some input phase that was mismatched. It had some different frequency from the VCO, and it also had some different phase from the VCO. So when we're trying to figure out what the error is going to be in the S domain, and once we've found the error in the S domain, we can convert it to the error in the time domain. So we're going to need to get this into a Laplace form. So let's start multiplying this through. We're going to multiply this term through here and here, and then we're going to eliminate some of these terms, right? These ones and this one are going to go away. We can then rewrite this first term, collect those together, right? Because it's multiplying by 1 over something. And we want to know what the error is in the time domain. And we have this expression in the S domain. The current form is not that easy to convert into time domain, and there's kind of a problem with it. And it's going to come specifically from this term. So we're going to have to pull out some old algebra tricks. And what we're going to do is we're going to use a partial fraction decomposition so that we can get this from the S domain back into the time domain. And we're going to do the partial fraction decomposition on this. And we can rewrite this. We know that there's two fractions that were summed together that could add up to this. And what we don't know, though, is what A prime and B prime are. So the phase error is going to take this form, but we just don't know yet what A prime and B prime are. So let's focus on finding A prime and B prime. So to find A prime and B prime, let's multiply both sides by S times quantity S plus AK. And that's going to cause some cancellations, right, on each side. And it's going to reduce this a little bit. Oops, and I think I forgot this should have been AK as well, so we can cancel the top and bottom. Now we have this term, we see a bunch of 1s on the bottom, so now we're going to get it down so that it's just all numerator, no denominator left. All right, so we're in a form now where we should be able to use this to find A prime and B prime. So to find these, right, often we have one equation but two unknowns. So what we're going to do is we're going to make a so-called educated guess and check. So first we're going to try S, and we're going to try that because we can visually see that if we choose s equals 0, it's going to make this term go away, but this one's going to be left. So we should be able to solve for a this way. So solving for a, we're going to input s equals 0, makes that b prime term go away, and now we're left with pretty clearly with something that we can solve for a prime, and we can see that a prime is quantity omega naught minus omega c divided by ak. And again, this omega naught, right, this is the different frequency that is coming in at the input, and these are some constants related to our system. Now, let's try minus ak to see if we can use this to get b, right? Again, we're going to use this educated guess and check, and we can see that if we make this minus ak, it's going to make this whole term 0, so make it easy to solve for b. Okay, so I put in minus ak, that makes that a prime term go away, and then solving for b, we see that we're going to just divide that over, and it is b is basically just a negative of a prime. Okay, so now we're back to seeing what the error is in the S domain. We're going to use this S domain error to transform it into the time domain error. We figured out what these two things were, and we're going to plug those in. And now we see that this form is going to be easier to work with for the Laplace transform. So in the next video, we're going to complete that Laplace transform.